Welcome all of you. So now onwards we will really take a plunge into analysis of the NMR spectrum. So far I was giving you lots of concepts about multiplicity pattern, chemical shifts, varieties of interaction parameters, and especially I showed you how we get the multiplicity pattern when the one spin is interacting with the various other spins with the different coupling strengths, whether it is chemically equivalent, chemically non-equivalent, groups of coupled spins are there like CH2 coupled to CH3, CH2 coupled to individual CH. You have varieties of examples. And I also classified this spin system, coupled spin system into weak and strongly coupled. I gave the definition of what is a strongly coupled spin system and what is a weakly coupled spin system. And we took number of examples of them and I showed the spectra of strongly coupled, weakly coupled spin system. And I discussed in depth about the Popple nomenclature. It is a nomenclature given for the coupled spin system, especially spin half. Each coupled spin half is given a letter in alphabet. And if it is weakly coupled, it is written with one letter in the alphabet and another letter should be far away in the alphabet order, like AX means weakly coupled. The alphabet next to each other are strongly coupled, AB is very strongly coupled. And even more strongly coupled is when the chemical shifts are identical, we call it as A2. And if the chemical shifts are identical but coupling still be present with something else, we call it AA prime. So, number of such examples are there. We can have AB, A2, AX for 3 spin. For 3 spin we can have n number of possibilities like AMX, A3, AA prime, A double prime, AB prime, all those things we can think of, AB2, ABC, varieties of things. Why there is no point in discussing everything which has been discussed at stretch in some of the previous courses, but I just gave you a bit of example of how we can analyze this by how this nomenclature is important in understanding the spectral pattern, so that you know how to interpret. As I told you, for weakly coupled, easy to analyze, whereas strongly coupled, lines are not of equal intensity, appearance of spectrum itself is a completely different. You cannot analyze in a straightforward way. Very strongly coupled, you need to simulate, especially 3 spins or more, you have to simulate through computers and then only do it. Not possible to analyze in a straightforward way. With this, now we will go to the analysis of the 1D spectra of some molecules. First of all, we have to create what is called a family tree approach to generate the spectrum. We can hypothetically, so you can simulate a spectrum by using a family tree approach. This is done only for the weakly coupled spin case, not for strongly coupled case. I will give an example like this. We do not go into the detail of 1 or 2 examples we will give and go to the real example. For example, I will take a problem one. There is a CH proton. Assume in a molecule, CH proton is coupled to CH3 proton, group of CH3 with a coupling constant of 7 Hertz. And it is also coupled to CH is also coupled to CH2 X with a coupling constant of 5 Hertz. That means there are 3 groups of protons. A is coupled to M, A is also coupled to X, AM coupling is 7 Hertz, AS coupling is 5 Hertz. This is what I wanted to tell you. Now we can generate the multiplicity pattern for each of them. What is the multiplicity? And also I give you another information. CH3 is also coupled to CH2 with a coupling constant of 3 Hertz, 10 Hertz. That means we have 3 groups of protons coupled, maximum we can have is 3 couplings. Okay, AM, AX and MX, 3 couplings are there. All the information is given for you. And it is a weakly coupled. Take an example where they are very far away, well separated, generate the multiplicity pattern. We can do it for one or two of them and go to the other examples. How do you generate the multiplicity pattern for a CH proton? Using a family tree approach. Assume there is a CH proton is not coupled to anything else. Then it is going to be a singlet, it is a single peak. In the absence of any coupling, CH proton gives a single line. Now I am bringing in the coupling of A with X. I told you already AS coupling is 5 Hertz. Then because the CH3 group chemically equivalent, apply 2Na+1 rule, Pascal triangle. Then you are going to get a quartet of intensity 1331. The single peak became quartet of 1331 intensity. And now each line of this quartet is also split into a triplet because A is also coupled to CH2 with a coupling of JAM. That coupling of 7 Hertz is there. Then what will happen? Each line of this quartet is further split into a triplet. But remember, this is 7 Hertz coupling and each of them is split into a triplet of intensity 131 with coupling of 5 Hertz. Then what is going to happen now? Look at it, many of these lines will overlap. Okay. Now if you start it, this is a triplet 1 to 1 intensity, this peak. And other one again 1 to 1 intensity, but because this separation is 7 hertz and this separation is 5 hertz, you see there is a overlap, crossover. As a consequence, you will make mistake in analyzing multiplicity pattern. So, but you should know how to extract the multiplicity information from a given complex multiplex spectrum. And again another one. See, this is what it is. What do you call this pattern? We already discussed. Which is the larger coupling? Larger coupling is a quartet and rest is triplet. This pattern is called quartet of triplets. For a CH proton, for the condition which I have given you, you are going to get quartet of triplets. Let us go to the example of another one, CH2 proton, same molecule. We have, I told you CH2 is coupled to CH3 with 10 hertz coupling, and of course it is coupled to other one CH proton with 5 hertz. How do you generate the multiplicity pattern now? CH2 proton in the absence of any coupling is a singlet. It is split into a quartet because of CH3 with a coupling constant of 10 hertz. Of course, intensity as you know it is 1331 intensity. It is a quartet. It is further coupled to what? CH proton. What is that CH coupling? 5 hertz. And what is happening? CH, it is going to split each of these line into a doublet, but it is a single proton. So, it is going to split each of this line into a doublet. And doublet there is no overlap because this separation is 10 hertz and the coupling is only 5 hertz. So, there is no question of this getting overlapped because 5 hertz from the center 2.5 hertz here, 2.5 hertz here, there is no overlap, but everything is very clearly separated out, and this is a doublet, this is a doublet. What do you call this pattern? Largest coupling is quartets, other is doublet. So, it is called quartet of doublets. In a hypothetical example of a molecule, we can generate a spectrum like this. Of course, multiplicity for the CH3 group also we can do, finish with that. CH3 is coupled to CH2 and CH. In the absence of any coupling, again CH3 is a singlet. Now, I am going to bring the coupling to CH2 of 10 hertz. So, this line is going to become a triplet. Very clear? It is going to become a triplet. What will happen now? This CH3 is also coupled to CH. CH will split each of these line into a doublet. And that separation is 7 hertz, this is 10 hertz. So, you can work it out, and now it is going to be a very simple pattern. It is triplet of doublets, and this separation gives you 7 hertz, and here to your separation gives you the other coupling 10 hertz. So, this pattern is called triplet of doublets. Very easily you can generate like this. Of course, we can generate all these parameters like that. I do not want to go to this example. I will go into another example where we can synthesize. Okay, we will go to a real example where I am simulating proton, deuterium and carbon 13 spectra of a molecule called CH2D2, okay, dideuteromethane. We have to synthesize this spectrum, simulate it. Remember, this molecule has 3 NMR active nuclei, which are they? Proton, its spin is half, carbon 13 spin half, and deuterium spin is 1. There are 3 nuclei in CH2D2, small molecule, there are 3 NMR active nuclei. And what are the couplings you can think of? One is there can be a coupling between proton and deuterium, there can be a coupling between carbon and deuterium, there can also be a coupling between carbon and proton. So, 3 different couplings are there, and all the 3 are heteronuclei. We will not worry about the chemical shift differences. One comes at proton frequency, other at carbon frequency, one at deuterium frequency, all are different. So, individually we can take the spectrum for each of these nuclei. So, with this I give you some idea just for the simulation purpose. Idea is 1 bond coupling JCH is 125 hertz and 2 bond proton coupling is 12 hertz, and of course, if I know this JCH, I can calculate JCD. I will tell you later when we go. Of course, I already discussed when I discussed the coupling constant. So, I discussed quite a bit about HH coupling and everything. Maybe I did not work it out with an example, we will come to that later. Possibly in this analysis I will discuss. Later we will see that. When I have a JCH, I can calculate JCD, or if I have JCD, I can calculate JCH. So, I can give an example of JCD is this thing and JCH is given. Okay. With this, I will generate the spectrum. Remember, I am telling you carbon 13 is natural abundance. Natural abundance carbon is 1.1%, very weak in intensity. If there are 100 molecules of carbon 99 is carbon 12, only one molecule is carbon 13. That gives us a very weak intensity. They are called satellites. We can discuss that also later. But proton, now if I look at the proton spectrum of this molecule, it experiences two types of coupling. One is proton can couple to carbon, JCH is there. Proton can couple to deuterium, JHD is there. There are two couplings. And what is a pattern we are going to get for the proton spectrum? You should understand by now. Of course, when I am looking for proton, deuterium is 100% abundant because it is deuterated. I am looking at a deuterated one. It will split this proton into how many lines? Remember, deuterium spin is 1. These carbon and proton, these two are spin half nuclei. Deuterium spin is 1. So, what will happen? Put simply 2Ni plus 1 rule. 2Ni plus 1 rule. I is equal to 1. There are 2 deuterium, 2 into 2 plus 1, you will get 5 lines. So, coupling of proton with deuterium gives 5 lines. Of course, intensity pattern is different here, that can also be worked out later. But how you work it out intensity? This is a different type of Pascal triangle. There is also a Pascal triangle similar to what spin of nuclei. For spin 1, spin by 3 by 2 also is there. But very easily we can work it out here. Let us say one proton is split into a triplet by 1 deuterium, because deuterium spin is 1. It splits into 3 lines of equal intensity. Spin half nuclei split into 2, spin 1 will split into 3 lines, 1 deuterium. What will happen to the other deuterium? Other deuterium will split each of these lines into 3 lines. So, this is the center of this 3 lines, from this 3 lines, from this 3 lines. Now, add up the intensity, it turns out to be 1, 2, 3 to 1 intensity. That means, if proton is coupled to 2 deuterium, you are going to get 5 lines. But what is the intensity pattern? Intensity is 1, 2, 3 to 1. That is what you are going to get. If the proton is coupled to deuterium, you are going to get 5 lines of intensity 1, 2, 3 to 1. And this is how the spectrum comes. Proton is coupled to deuterium, and this should be the proton spectrum if I simulate it. Now, what is happening to carbon 13? Carbon 13 can also couple to proton with a coupling constant of 125 Hertz. But remember, abundance of this carbon is 1%, only very small 1.1%. As a consequence, then each of this line, because of carbon, split into 2 lines like 2 pentate. This is a pentate, let us consider a pentate. There will be 2 pentates separated from one this side, one this side. You are going to get peaks like this. You are going to get satellite like this. You see, small. This is because of coupling with proton. This is coupling with deuterium. This is coupling with carbon. Proton coupling with carbon. Intensity is only 1%. This is what happens. And now measure the separation of one of these peak to another peak. It is going to be JCH coupling. Measure to this any line to each corresponding line on the other side of the satellite. It gives you JCH coupling. So, this is how you are going to get the coupling information. You understood? So, each line of this thing is further split, and this is what the proton spectrum is like this. Okay? This is how the proton spectrum is going to split. Let us look at the carbon 13 spectrum of CH2D2. How does the carbon spectrum comes? Very easy. Carbon is split into a triplet because of H2, chemically equivalent spins. We have to get the intensity pattern 1:2:1. A triplet you are going to get. Then each line of the triplet is split into a pentate, a 5-line pattern because of deuterium coupling. This is what happens. So, CH coupling is there, DH coupling both are there. As a consequence, you are going to get a pattern like this. The overall pattern is 1 2 3 to 1 intensity, a quintet you are going to get, and the 13C spectrum really is like this. One, a triplet because of 1 JCH, direct coupling between carbon and proton, and each line of this is further split because of the deuterium coupling is like this, and this is how the pattern you are going to get. If you take the carbon 13 spectrum of this molecule, you will get 15 lines. This center of this to center of this gives you JCH. Any two adjacent lines you take, here you are going to get JCD. Okay. All right. And this is JHD and this is JCH you are going to get, fine. Now we will see the deuterium spectrum of this molecule, another nuclei. We saw how the carbon spectrum comes, we saw how the proton spectrum comes. Let us now try to understand the deuterium spectrum. Deuterium spectrum is a triplet because of protons, of course, and spin off nuclei. It will be a triplet, and each line of the triplet is further split into a doublet because of carbon 13. Okay, it appears as satellites. See, now I give you a value for JHH, JHD and JCD just to see that if you simulate how that is the spectrum come. First of all, it is going to be a triplet. Proton, deuterium coupled to proton will be a triplet, and the coupling is very small. JHD coupling is only 1.94, but I have written like this just to make you understand. I got a triplet, but what is happening is each line of this triplet is split by carbon 13, and then this what happens, it is a satellite. But remember, this carbon 13 is a doublet with a satellite, and this coupling is quite larger than this. So, it appears as if it is overlapped, moves on either side. See, this is another one, this is another. Each of these line is split into doublet with a very weak intensity peaks. They are called satellites. The real spectrum of deuterium is like triplet and 3 satellites on either side, and they appear as satellites. So, very simple. How looking at the spectrum of the simple molecule appears simple, CH2D2, but look at the spectrum we are going to get. Carbon 13 spectrum is different type, proton is different type, deuterium spectrum is different, all are different because spins are different. One is low abundant carbon 13 that appears as a satellite. When you look at proton, deuterium is going to give quintet. When you look at deuterium, proton will split this into a triplet, and for each of these lines carbon splits them into triplet. When you directly observe carbon, is a different question, satellite question does not arise. When you observe carbon, proton split this into a triplet, and each line of the triplet splits into a quintet because of deuterium. Fantastic way of understanding the spectrum. Very simple molecule, 3 different nuclei give 3 different types of spectra. Okay, now we will go to the first order analysis of the real spectrum. I am looking at the spectrum of a molecule like this, hypothetical or real molecule does not matter, and this is the spectrum. Now, how do we interpret it? I have started with a very simple molecule just to make you understand, and of course, you should use your knowledge of chemistry like chemical shift and coupling constant to interpret this one. Where does Ca3 come? I have always been telling you, when I discuss about the chemical shift also, I told you Ca3 is more shielded, it comes to the high field. Normally, unless it is attached to oxygen or nitrogen like that, Ca3 will always resonate at the higher field. One peak coming here is a Ca3, that is my assumption. How do you know it is Ca3? If it is Ca3, if it is coupled to CH2, it has to be a triplet, correct? It has to be a triplet. So, as a consequence, I would say this is a Ca3 which is coupled to this CH2. Why not this Ca3? There are 2 Ca3s here, but remember this CH3 is attached to CH, that will only split this into a doublet. This CH will split this CH into a doublet. Since it is a triplet, this cannot be this Ca3, this has to be Ca3 proton 4. I can easily assign. I will that number 4 I can assign for this peak. Then obviously other CH I know. This has to be other CH because this is coupled to CH and it has to be a doublet. So, this is a proton 1. Then what is the next one? one is CH2, other is CH. Interestingly, both of them will give rise to quartet, because CH3 will split this into quartet, this CH3 will split this into quartet. There are 2 quartets. Now tell me which is the CH2, which is CH. First you have to think of this separation and separation of one of them should match. That is the coupling between CH2 and CH3, and this separation and separation of one of these J coupling should match, that is another CH3. We can identify. Simplest possible way, look at the intensity. This is 1, this is 2, 2 is to 1. Obviously this has to be CH2, double the intensity. This is proton 3, this is proton 2, because intensity is half of that. Another way is you measure the separation here, J coupling, see which it matches, whether this or this, then you know what is that one. Very easily you can make the analysis. So you can look at the chemical sheet, look at the intensity pattern, and look at the multiplicity patterns, measure the coupling. Using all these 3 information, you can analyze the spectrum very easily. And if you analyze this, and this is how it comes, this is proton 1, this is proton 2, this is proton 3, this is proton 4, very easily. So very easily we can analyze this one. Okay. Next we will go to another molecule. What is the other molecule? This one. This spectrum is simple. Again, this is a first order analysis. Remember, it is a first order analysis. Means they are weakly coupled. It is not strongly coupled. So first order analysis means straight away you can get the chemical shift and coupling constants. Direct assignment can be made without resorting to numerical simulations or anything. That means first count the number of individual chemically inequivalent protons in the molecule. There are 1, 2, 3, 4, 5, 6. There are 6 groups of protons in the molecule. How many groups of peaks are there? There are 6 groups of peaks here. You can understand. Now start interpreting. Of course, these 2 have to be triplet. It is because of this CH3 and this CH3. Why it is a triplet? Because each of the CH3 is attached to CH2. This CH2 will split this into a triplet. This CH2 will split this into a triplet. There are 2 triplets on high field. As a consequence, this has to be 2 CH3s. Which is 1 and which is 6 is a matter that we have to discuss. As I already told you, you have to look at the separation of this J coupling of this and match with other one with to which it is coupled to. You can extract that information. Easy to analyze. If it is all of them, let us say both of them are equal J coupling. Still if you want to know which is which, there are ways to analyze. When you go ahead further, we can find out by using Cauchy and other 2-dimensional techniques. But we do not have to go to that one. In this is a fairly simple molecule, straight away we can get this information. Okay. Now what is the next easiest analysis you can make? Easiest analysis next is 5, because 5 is coupled only to CH2. I am sorry, CH3. When it is coupled to CH3, what is the pattern you expect for 5? It has to be a quartet. Where is the quartet here? Only a quartet is here. This has to be proton 5. All others are not quartet. Their multiplicity is different. Now come to these 3 protons. How do you interpret it? What about this one? That can couple to this proton 3 CH2, and it has to be a triplet. Where is the triplet you can think of? See, one is, of course, this triplet is methyl, we know that. Where is the other triplet we can think of? It is here. And also very interestingly, it is attached to oxygen. As a consequence, it has to move to the downfield. Very easily you can assign this one. So this has to be, my first guess is, this should be proton 4. I have analyzed 1,6, this is a proton 5, this is proton 4. Now what are left? 2 and 3. In the 2 and 3, which one is more complex? 2 or 3? Look at it. Which is more complex? The more complex is proton 2. Why? The reason is, this proton 2 is split into a quartet because of the CH3, and each line of the quartet is split into a triplet because of this. So it is a more complex pattern. What about this one? This one is split into a triplet because of this, and each line of the triplet is further split into a triplet because of this. So more complex pattern is this of the 2. Obviously I will say this is 2. This is compared to this is less complex. I would say this is proton 3. So, now we can easily interpret just by looking at the multiplicity pattern, and we know where the peak will resonate. So, very easily this sextet has to be proton 2, this quintet has to be proton 3, and this has to be proton 2, and this is 5. That is what I said. So, very easily we could interpret this molecule. A very simple molecule, fairly easy to interpret. This is a first order analysis of the proton spectra. We will go to a little bigger molecule. As the molecule size increases, the complexity becomes more and more. Look at this molecule. Where do you start with? Always count the number of chemically inequivalent protons. There are 1, 2, 3, 4, 5, 6. I have numbered it, but forget about 6. There are 1, 2, 3, 4, 5, 6, 7. 7 groups of protons are there. Which are the 7 here? See 1, 2, 3, 4, 5, 6, 7. Very easily you can find out. Very fact they are well separated. Chemical shifts are far away separated between themselves. I would say it is weakly coupled. So, first order analysis should be easily possible to do. We will assume first order analysis we can do. Now, what is the first one you can think of? Always look for the high field. High field is Ca3. This Ca3 can couple to this CH2 and become a triplet. So, this is a triplet. This has to be proton 8. My first guess is right. Then this one will become what? Has to be a quartet. Where is a quartet you can think of in this case? All are of multiplicity pattern is more except this one. This is a quartet. This has to be proton 7. This also agrees with the our this thing chemistry information, because it attaches C double bond O and O. This is electronegative. It will withdraw this, get more D shielded, comes at the low frequency region. I am sorry, this high frequency region, low field region. This is what happens. So, easily you ascend S 8 and ascend 7. What are the remaining? Remaining you can still think carefully. One of them, look at this proton. This is coupled to only this one. What is the pattern you think of for it? It has to be a triplet, because this is coupled only to this, nothing else. And further it is attached to bromine, which is electronegative. So, it comes to the downfield, low field region. And low field you see where is the triplet? This is the only triplet possible. So, for my first guess is this could be proton 1. I have answered 8, 7 and 1. What is the remaining thing we can think of? Where is another triplet? Look at this one. This is one possibility, this is coupled only to this, nothing else. There is no long range coupling. So, this also has to be a triplet, because it is split into a triplet because of proton 4. Where is the next triplet? See here, I will say this is proton 5. That is also correct. So, I could assign all these things very easily. Next interesting point comes is this proton experiences triplet because of this, becomes triplet because of this. Each of the CH2s here experiences coupling with the other two CH2 sitting on either side. Look at this molecule. This CH2 is split into triplet because of this, and each line of this triplet is split into another triplet because of this. For this one, look at this one. This is again split sitting between two CH2s. Again this will become triplet of triplet. What about this one? This is sitting between two CH2s. As a consequence, this is also triplet of triplets. See, this is the pattern you are going to get for these of them. Almost identical pattern. Look at this one. Now, how do you say which is 2, which is 3 and which is 4? What is the logic you apply? Pattern is similar. All of them are independent, but there is a difference in the chemical shift. But why chemical shift comes? Of course, you can apply the induction effect. Because of this, this will be more low field, and this is further low field, like that. You can start for this one induction effect, this will be next, like that. You can apply some chemistry rule and find out using the induction effect what is what. Okay, we will make a rough guess using our chemistry knowledge and find out what is what. This is the first my assumption 8 Ca3, then this is 7, that is what I said, it is a quartet, this is a triplet, and I said this is 1 because it is only a triplet, that is also correct. Then I said this is a triplet 5 because there is the only possibility for a triplet. Then I said this is triple after triplet. I put this as 2 because I assume that there is more induction effect comes to downfield. That is also possible. Then I said this is 4. This comes downfield because of induction effect. This is more electronegative here. So I would say this one. And last one I would say this is coming here because this is far away from bominant C double bond O. So it resonates here. This is my assignment. How are you sure it is my assignment is correct or not? For this, one way is you have to do selective decoupling. Each proton break the coupling of one of them with the other and find out where is the change you are observing. That was the thing which people used to do about 30-40 years back. Nowadays it is not done. That is you can easily identify by what is called 2-dimensional NMR. Then you will easily come to know which is coupled to is, and you can find out and track it, and easily we can make the assignment. We will come to that when I come to 2D NMR later. But right now what I wanted to tell you is, in a weakly coupled spin system like this, if you just have the spectrum like this, just find out the number of chemically inequivalent protons, look at the multiplicity pattern, apply your knowledge of little bit of chemistry with electron, electron negativity atom, electron donating group is there, withdrawing group is there, whether it is shielded, de-shielded, use some idea. And then third point, measure the intensity of the peaks, then easily you can measure it, you can make the assignment. So this is what we did, and we can go further and start making the assignment. Since the time is up, I am going to stop here. We will get lot more examples tomorrow. Next class, lot more examples we will take. But today what I wanted to tell you is, we really jumped into the analysis of the proton spectra. This is the main aim of this course, to make you more comfortable. If a spectrum is given of any nuclei for that matter, how do you interpret it? What is the idea you have to do apply? How do you go ahead in interpreting this? What I wanted to discuss. And we simulated the spectrum using a family tree approach for some hypothetical molecules. And I took the CH2D2, a simple molecule, where 3 different nuclei, there 2 spin off and 1 spin 1. We simulated the spectrum for each of them. We saw how when it is coupled to other nuclei, spectrum changes. What type of spectra we get for carbon, proton and deuterium we observed. And then a realistic example of some of the molecules I took. Starting with a simple molecule, then little bit complexity keeps increasing. We will go ahead further, we will take few more examples. As the complexity increases, how it comes we will see. Finally, we will understand, and of course by the end of this course, you must be comfortable enough to interpret the spectrum in a better way. I will stop at this stage. Thank you very much.